This is a lecture on waves recorded in 2 parts. Welcome to the study of waves. What is a wave? A wave is a disturbance, and this disturbance may be propagated with or without a medium. So, wave is a disturbance that moves from one point, the point of origin, and it moves outwards. So it is the propagation of energy. But there are 3 types of waves. Mechanical waves require a material medium, and so mechanical waves transfer energy and momentum through the material medium. But electromagnetic waves do not require any material medium. So they are the oscillations that are oscillations of the electric and magnetic fields that can even propagate through space and that do not require a material medium. A third kind of a wave is called a matter wave. Now, matter waves are waves associated with electrons, protons, neutrons, etc., or rather the waves associated with fundamental particles. So those are the 3 types of waves. Now here is a diagram that shows you the types of waves. So you have mechanical waves, and the best example of a mechanical wave is a sound wave. You have electromagnetic waves that do not require a material. The example is a light wave or X-rays, radio waves, etc. And then you have matter waves, and an example is the waves associated with an electron. Now in this chapter, we will primarily focus on mechanical waves. And we will do the study of electromagnetic waves after we understand electric and magnetic fields. By the by, this diagram here represents the production of electricity using the power in a wave. So you have a floating device that bobs up and down with the waves, and that motion is converted into a rotational motion. Down here at the bottom of the ocean, you have the rotational motion powering an electric generator that produces electricity. So that is what the diagram represents there. Before we continue further, let us look at the characteristics of a wave. Some definitions that you have to know. First of all, every wave has a wavelength, which is connected to its frequency. We're going to see that. Then you have the amplitude, time period, and frequency. And these are the wavelength is represented by the Greek letter lambda, that is lambda, and is measured in meters. Amplitude by a capital A. Amplitude is a displacement, so it's measured in meters again. Time period is of course in seconds, and frequency is 1 by time period, which is 1 by second, which is also called hertz. Now the wave velocity is simply the product of frequency and wavelength. And that comes by the definition of wavelength. Now what is wavelength? Wavelength is the length of a wave. And frequency is the number of such waves in 1 second. So for example, if the length of a wave is 10 meters, and you have 5 such waves in a second, the total displacement is 5 times 10. And so that's why the velocity of a wave, which is the displacement in a second, is the frequency multiplied by the wavelength. As we can see here, This is the wavelength, that's the length of a wave. And the amplitude is the maximum displacement from the equilibrium position. That is the equilibrium position. Now this represents a transverse wave. This is called the crest. This point is called the trough. So those are the basic definitions, and this relation is a very important one. Now, as explained, this diagram shows that this is 2 times the amplitude, because that's the amplitude. And a wavelength is the length of a wave, which is also the distance between 2 consecutive crests or between 2 consecutive troughs. And this is the velocity of the wave, which is the velocity with which energy moves through the material. And again, velocity is the product of frequency and wavelength. But since frequency is 1 by time period, it can also be written as wavelength over period. Now, based on the direction in which energy is propagating and the vibration of the particles of the material, we can define 2 types of waves. One is a transverse wave. In this transverse wave, the disturbance or the vibration of the particles is perpendicular to the direction of propagation of energy. So if energy moves along the x-axis, the disturbance moves along the y-axis as shown here. So energy moves along the x-axis and the disturbance or particle vibrations are along the y-axis, which means they are mutually perpendicular to each other. Now, light is a transverse wave. Although it's an electromagnetic wave, it's a transverse wave. We'll see that later on. Now, the second type of a wave is a longitudinal wave. The word longitudinal means lengthwise. In this case, the disturbance and the direction of propagation are both in the same direction. They are parallel to each other. So if the energy is moving along the x-axis, the disturbance is also moving along the x-axis. Now you need to understand that waves may be a mix of these two. For example, waves in the ocean, water waves, are not perfectly transverse nor longitudinal. They are a mixture of both transverse and longitudinal waves. And this diagram here shows a slinky in which you could produce a transverse wave or you could produce a longitudinal wave. So those are the 2 types of waves. I've given examples here. A transverse wave is a wave in a guitar string. Longitudinal waves are sound waves in a fluid, which means sound waves propagating through air. And as explained before, a combination of these may be the ocean waves. This diagram represents a longitudinal wave through a spring, through a stretch spring, in fact. And we are focusing our attention on this black dot here. This is the equilibrium position of the dot at t is equal to 0. And then this one, as the wave travels outward, the dot moves back and forth between the equilibrium positions. So it starts from here, goes back to one amplitude position, returns to the equilibrium, again to the next amplitude, and back again, as you can see. This is at t is equal to 0. This is after a certain time, half the time period later, and then after a full time period, you see that it returns to where it was. Take a look at this. So in one time period, it's gone from here, there, and back again, as you can see. So that's the representation of a longitudinal wave. Now let us take a look at a transverse wave shown at 2 instants of time. And this is how the wave was at t is equal to 0 seconds. And this is how it is when time is equal to 3 seconds. So the same wave, a snapshot of the wave at two different times, it's 0 seconds and 3 seconds. And then you can see that this is the wavelength as defined before. And here we're trying to find relationships between the wavelength and frequency and velocity. Here you can see that this point has moved over to here. So that means the displacement is 8 minus 2, which is 6 centimeters. And the time taken is, of course, 3 seconds. So the velocity of the wave is 2 centimeters per second. And the wavelength, as you can see from here, this is 10, this is 2, so the wavelength is 8 centimeters. And therefore, from the equation, velocity is frequency times wavelength, you can find the frequency. Because we know that the velocity is 2 and the wavelength is 8. You find that the frequency is 0.25 hertz. What is the time period? Remember that time period is the reciprocal of frequency, so it will be 1 by 0.25 hertz, which will be 4 seconds. I also want to mention at this point that the amplitude is 6 centimeters. Remember, this is the amplitude, and you can clearly see that it is 6 centimeters. Now here we're looking at a pulse. And it's actually a wave, which is a single disturbance that moves through the medium with a constant amplitude. So it's just a single disturbance that moves through the medium with a constant velocity. And of course, the displacement at any point, delta x, is given by that constant velocity multiplied by the time. And now this diagram represents snapshots of a transverse wave moving through a string under tension. And you see colored dots, and the same colored dots represent one wavelength apart. So whenever you see two dots having the same color, the distance between them is one wavelength apart. For example, here you have green, and again you have green here, so this distance is one wavelength apart. And the snapshots are taken for the first one at time t is equal to caps t, that's one time period. Then this is taken 1/8 of a time period later. And then this is 2/8 of a time period later, and so on, until we come to 8/8 of a time period later, which makes it 2 times the time period. So t plus 2t. So t plus t, I mean 2t. So you can see how the energy moves out into the medium as time passes. Look at this, and I think it's very clear that energy is moving outwards into the medium. And what's most important is to understand that in one time period, you have one wave created. So each time period, you have one additional wave created. So that's very clear. If you look at this, you have one wave here, but when you come down to the second one, you have 2 waves. So you can see that each time period gives rise to an additional wave. It is important to understand that at this point we are looking at a one-dimensional wave. It's only moving along one axis, for example, the x-axis. And we're trying to find an equation, a mathematical representation for this one-dimensional wave. If you look at the waves, you understand that it is a sine function. A sine function, typically varies between +1 and -1 and repeats itself. And so that is a sine wave. So the representation of this is going to be a sine wave. This also means that one wavelength lambda is equal to one rotation, which is 2 pi radians. I hope you get that. So one wavelength is equal to one rotation, which is 2 pi radians. Therefore, if we are looking at an angle theta and the distance is x, the ratio theta by x should give us 2 pi by lambda, because 2 pi is the angle for wavelength lambda. So theta by x is equal to 2 pi by lambda. Now this is an important relation between theta, which is the phase, and x, which is the path. So to get the phase, you multiply the path with 2 pi by lambda. Now, in trying to find the equation, remember that we are looking for the representation of displacement along the y-axis as a function of x. So depending on what point we are looking at, how far away from the origin we are, y is going to be different. For example, when x is equal to 0, in this case y is equal to 0. And when x is equal to half the wavelength, again y is 0. And when x is equal to 2 pi, again y is equal to 0. I hope you're getting what I'm trying to say. Now look at this x. This is lambda by 4. That's 1/4 of this wavelength, isn't it? 1/4 of this wavelength. And you see that y is a maximum. Again, y is a maximum at 3/4 of the wavelength. So you see that y is a function of x. And this can be represented as the amplitude A sine 2 pi by lambda times x. Now that should be clear, because in this equation, if you substitute x is equal to 0, you're going to get sine 0, which is 0. So you get y is 0. So we're looking at this point now. When x is 0, y is 0. But if you substitute x as, let's say, lambda by 4, lambda by 4, I'm not writing that, but you can see that the lambdas will cancel out, and then you have 2 pi by 4, which is pi by 2, and sine pi by 2, which is 90 degrees, is 1. So y is equal to a times 1, which is a. So we're looking at this point. When x is lambda by 4, 1/4 of the wavelength, y is a. So I think that's very clear enough. And so we go to, if we bring in the time factor, and we're looking at one of the points, x distance away, but at a later time, t seconds later, y is going to be different because the energy is moving out. So now, considering y as a function of both x and t, going to have to say sine 2 pi by lambda x minus vt. Now why? Because during that time t, energy has moved out by a displacement equal to velocity multiplied by time. So to get the displacement, you got to take the difference between the x and the difference in the distance, which is the displacement. So now we have, if you distribute this term 2 pi by lambda, you're going to get 2 pi by lambda times x minus 2 pi by lambda times vt. That's interesting, because now you can see that you have two terms essentially. Let's focus on this one. You have v by lambda here, v by lambda, and v by lambda is actually f, because v is f lambda, right? So v by lambda is the frequency. So here you have 2 pi times frequency, 2 pi f. All right, so now we can rewrite this equation keeping that in mind. So a sine, I'm going to call this k, 2 pi by lambda is k, and 2 pi by f, 2 pi times f, 2 pi times f is omega. Let me say that again. V by lambda is f, frequency, and 2 pi times f is omega. So you have the equation for a progressive wave. A progressive wave is a wave that progresses or moves outwards. And this is for a one-dimensional wave. This is the neat little form in which you write that. And here you have two constants. K is called the wave number. K is 2 pi by lambda. And K is the wave number. Very important constant. Omega is angular velocity, 2 pi f, or 2 pi by t. And then another interesting thing is that if you divide omega by k, so you divide the right-hand sides, see what you're going to get. 2 pi v by lambda times lambda by 2 pi. 2 pi's cancel out, the lambdas cancel out, and you're going to get the velocity. That means to find the velocity of a wave, you divide the wave number, divide the angular velocity by the wave number. Angular velocity divided by wave number gives the velocity of a wave. Let us now work out an example which is given in the textbook, just to make clear what we've been talking about. Here you have snapshots, two snapshots at two different times. As you can see, one represented by the dotted line and the other by the unbroken line. And the distance here is calculated from the speed of the wave multiplied by the time. Displacement is velocity multiplied by time to show that. But first things first, let's look at the equation of this wave. The equation of this wave is 0.2. What's the 0.2? 0.2 is the amplitude, right? 0.2, that's in meters now. That is the amplitude. 6.28x, so that is the K. And how do we find that? Based on the diagram, we can find out the lambda. Because remember, lambda is the wavelength. You can find out the lambda. And 2 pi divided by that lambda gives you 6.28. And then minus 1.57 t. And I also forgot to mention that this is the equation of a wave that is moving along the positive x-axis. Positive x-axis. What if it was a wave moving in the opposite direction along the negative y-axis, negative x-axis? Well, the only difference would be you change the negative here into a positive. So keep that in mind. So coming back and comparing this equation of the wave with the general equation, which is sine kx minus omega t, immediately you see that A is 0.2 meter, K is 6.28, and the unit of wave number is meter raised to minus 1. Let me at this point tell you that wave number is actually the number of waves in 1 meter. Let's stop there. The number of waves in 1 meter. So if the wavelength is 1 meter, then how many waves do you have in a meter? Just one. But if the wavelength is half a meter, then you have 2 waves in 1 meter. Is that clear? So the wave number is then 2. So that's what wave number is. And then going back, omega by comparison here is 1.57, and the unit is either radians per second or just per second. And then remember, you can find the speed of the wave dividing omega by k. And so when you do that, look at the units. It comes out to be meter per second, and you get 0.25 meter per second. Now we can work backwards to find lambda, because we know k is 2 pi by lambda, and so lambda is 2 pi by 6.28, and you get lambda as 1 meter. Wait a minute, is this wavelength 1 meter? Let's check it out. If you go from this point to the corresponding point which is one wavelength apart, you see, yes, it's 1 meter because that's 1.7 and that is 0.7. So the wavelength is 1 meter, 1.0 meter to be specific. So I hope this example has cleared things up as to how to connect the terms associated with a progressive wave in one dimension. Next, we're going to take this one step ahead and find what is called the linear wave equation. Getting to know how we get the linear wave equation is as important as the equation itself. So let's take it one step at a time, finding the linear wave equation. First of all, we know that y is equal to a sine kx minus omega t is the wave equation for a wave that moves along one dimension along the positive x-axis. So if you take the partial derivative of this with respect to, so again, that's a function of x and t, take it with respect to time, you get minus a omega cos kx minus omega t. Yeah, because the derivative of a sine function is a negative. Oh, here, yeah, there's a negative there because we're taking it with respect to time, okay? So we're taking it with respect to time, that's why. And then if you do this a second time, you get dou squared y by dou t squared, and you now go back to a sine function, but there is an omega squared because you got to write that omega one more time. And remember that in this particular first case, we are holding x a constant. That means we're looking at y at a particular position x. All right, we are not changing x. So that's how you get that equation. Now, if you do the opposite, so if we now take the partial derivative with x holding time constant, right? So you have dy by dx now. Then you're going to look at the x factor, which is kx. So you got to write the k outside. So it's going to be ak cosine kx minus omega t. Remember, we're starting with the sine function, and that's why you get a cosine there, and there is no negative because this is a positive quantity. I think that's clear. So doing it a second time, now of course you're going to get a negative a k squared sine kx minus omega t. And remember, we get this holding t constant. Now that's equation 1. This is equation 2. If we divide equation 1 by equation 2, on the left hand side, this is what we get. And on the right hand side, you're going to get omega squared by k squared. Because on the right hand side, everything else, you can see, cancels out. You have the same sine kx minus omega t, and a cancels out, so you get that. And omega by k is the velocity, so omega squared by k squared is obviously velocity squared. Which means d squared by dt squared, I'm just rearranging that, is velocity squared d squared y by dx squared. This is called the linear wave equation. Very important. So d squared y by dt squared is v squared d squared y by dx squared is the linear wave equation. We're going to use that as we continue, so hold on to that. The next step is important because we're also going to do this in the lab as one of our first labs. We are trying to find the speed of a wave through a stretched string. Now, a stretched string could be a guitar string because it's under tension. There is a force acting. it has a particular length. And you know that in a guitar there are different strings and they have different radii. They have different thicknesses, so to say. So you have a thinner string and you have a thick string. So an important quantity that comes into effect here is the mass of 1 meter of the string. Now that quantity is called the linear density, mu. So if you take however much of a string, like let's say 10 meters of a string, and the mass is 10 grams. So 10 meters have a mass of 10 grams. Then of course 1 meter has the mass of 1 gram, well, which should be in kilograms. So that's what you mean by mu. Mu is 1 gram per meter. And therefore, if you take any particular section of the string, to find its mass, you just multiply the mu with the distance. So that's what is given here. So let's try to find the wave speed on a stretched string. Mu is the total mass of the string divided by the total length. Its unit is kilogram per meter. Ft is the tension. Usually you have one end of the string tied to a rigid support, and at the other end you have a weight hanging. So we know that if that weight is like 1 kilogram, we know the tension is 9.8 Newton. So that's what you mean by Ft. So this string is under a tension and it has a linear density mu, and we're trying to find the speed through the string. Now to find the speed through the string, if you take a close look at a small section of the string, as it is as the waves are moving along, or as the string is vibrating, we see that at this particular point there are two forces acting. One is the tension Ft, the other is the force F1 that's acting on that particle down. Remember, the particles are moving up and down, correct? The wave itself is moving along the x-axis, the particles are moving along the y. So this particle is acted upon by two forces. One is the tension of the string, the other is the force acting on the particle at that point. Okay, and F1 is F1 changes, it's a variable. So if you look at this section or another particle close by, delta x distance away, you find that the tension is the same, but now in that direction, and then F2 is the force acting on that particle. If you take the slope at these 2 points, remember slope is dy by dx. dy by dx, you're going to get the slope here as negative F1, because you know that's downwards, negative F1 by Ft. Here you're going to get the slope as Ft by F2. So we're going to write down the slope at both those points. And like I said, slope is change in y by change in x. So that's what we're going to do. So F1 by Ft is negative dy by dx because F1 is down. But F2 by Ft is, well, I'm going to remove that negative. It's actually dy by dx. So those are the two slopes. Therefore, the net force acting on that section, net force is the sum of the two forces. So the net force acting on that section is just the sum of F1 and F2. Simply substitute. Ft is common, taken out. And then you have negative. Now I got to remember that that's positive. I've corrected it. So that's positive minus this, okay? And according to Newton's second law, net force is equal to mass times acceleration, isn't it? So we're talking about the mass of that section, which has a length delta x. And as before, we know that the mass is just mu times delta x. So, and A, acceleration is d squared y by dt squared. So that's what I've done. Now, rearrange that, or rather divide by Ft times delta x on both sides. Ft times delta x. So when you divide by Ft times delta x on this left side, you're going to get ft cancelled out and you have a delta x here, but on the right side delta x is going to get cancelled and you're going to have an ft down there. Okay. Okay, now if you consider that this section is really small, which means delta x tends to 0, then the numerator is going to change here. The entire left-hand side is going to change to d squared y by dx squared. Because x2 and x1 are like now 1 point, so you're going to get d squared y by dx squared is equal to, and on the right side, mu by ft d squared y by dt squared. But remember that we have a very important relation where d squared y by dt squared is equal to v squared times d squared y by dx squared, as we saw. So now we're going to compare that equation, compare this equation with this one. When you compare, this is kind of backwards, so you have to look at that carefully. Here you have d squared y by dx squared. So if I were to write it, I don't think, you can easily make it out. It's going to be 1 by v squared d squared by dt squared, okay? Anyway, when you compare the two relations, you're going to see that v squared is ft by mu. And that means velocity is square root ft by mu. Very important relation again. So the velocity or the speed of waves through a stretched string is the square root of the tension divided by the linear density. What does that mean? That means if you increase the tension, the speed is going to increase. And also means that if you decrease the linear density, that means for a thinner string, the speed is going to be much bigger. So those are the two factors on which the speed of waves through a stretched string depends. Well, I'm going to end this portion of the lecture here because I have decided to do this in 2 parts. I don't want this to be too long. It's already taken up about 37 minutes. So this probably the second part could be taught in class, but I want everybody to do this first part from the YouTube video and answer the assignment questions, because that's going to be taken for a grade. This is to make up the day today that has been lost. Thank you, and hopefully we'll see you in class on Thursday.